Calculus with parametric curves. First, let's talk about how to get the slope of a tangent line when given parametric equations. Suppose we have the parametric equations x equals f of t and y is equal to g of t. And we will also assume for the time being that y is some function of x. Well, if y is g of t, we can replace y here with g of t. And then we have capital F of x, but if x is lowercase f of t, we can replace x with that. Taking the derivative with respect to t, we get g prime of t is equal to, and then the chain rule tells us that here we get f prime, that's capital F prime, of the inside function, multiplied by the derivative of the inside function. Now if we divide both sides by f prime of t, we get cancellation here, and we have g prime of t divided by f prime of t is equal to capital F prime of f of t, but now let's remember that f of t is x, so that's just capital F prime of x, but capital F prime of x is dy dx. And so in the end here, we have dy dx is equal to g prime of t. G prime of t is the same as dy dt, divided by f prime of t, which is the same as dx dt. And so we have the formula dy dx is equal to dy dt divided by dx dt. And you can see that summarized here. Now again, this is only valid if dx dt is not equal to 0 because we're not allowed to divide by 0. For concavity, we need the second derivative. And we know the second derivative of y with respect to x is the derivative with respect to x of the first derivative. But dy dx is also a function of t. So the derivative of this function of t is the derivative with respect to t of that, but then we have to divide by dx dt once again. And so it's very much like the formula for the first derivative, where we have to divide by dx dt. So we are simply taking the derivative of the new function that we're talking about, so the derivative of the derivative, but then we have to divide by dx dt again. Let's take a look at an example. Suppose a curve C is defined by the parametric equations x equals t squared and y equals t cubed minus 3t. First, let's show that C has two tangents at the point 3, 0 and find both of their equations. First, we need to find the first derivative, dy dx. To get dy dx, we need to take dy dt and divide it by dx dt. So let's go ahead and calculate dy dt. So if y is equal to t cubed minus 3t, dy dt is 3t squared minus 3. And so that is our numerator. And we're going to divide that by dx dt, and dx dt is going to be 2t. So now how do we show that this curve C has two tangents at the point 3, 0? Well, let's think about what happens at the point 3, 0. So when we say the point 3, 0, we mean that x equals 3 and y equals 0. But in the parametric form, if x equals 3, that means that t squared is equal to 3, right? Because x is t squared. So if I just replace x with t squared, I get this. And y is t cubed minus 3t. So when we say y equals 0, we have t cubed minus 3t is equal to 0. Now I'm going to solve both of these equations. In the first equation, I get t equals plus or minus the square root of 3. And in the second equation, we can factor out a t, and then we can set both of these equal to 0, and you can see that we get t equals 0, and then here we get t equals plus or minus 3. Now we're only going to take the values that these have in common, because x has to be 3 at the same time that y has to be 0. So although y is 0 when t equals 0, x is not 3 when t equals 0. So we exclude this value of t. So we can see that there are two values of t for which the curve passes through the point 3, 0. So now what we'll do is we will find the slope of the tangent line for each of those values of t. So I'm going to find the slope when t is equal to negative radical 3, and I'm going to find the slope when t is equal to positive radical 3. And to do this, we are just going to take the derivative dy dx and evaluate it when t equals negative radical 3, and likewise take the derivative dy dx and evaluate it when t equals positive radical 3. And so all we need to do now is plug positive radical 3 and negative radical 3 into the first derivative here. And in doing that, when t equals negative radical 3, we get this. And when t equals positive radical 3, we get this. And let's go ahead and simplify those. So this first one is going to be 3 times 3 is 9, take away 3 is 6, divided by negative 2 radical 3. This is negative 3 divided by radical 3, which is the same as negative radical 3. And the other one here is going to be 9 minus 3 is 6, divided by 2 radical 3. And this is 3 divided by radical 3, which is radical 3. And just a quick note about simplifying 3 divided by radical 3. All we have to do here is multiply by a radical 3 in the numerator and the denominator. And this gives us 3 radical 3 divided by 3, and then the 3's cancel out. And so that's how I'm getting both of these values here. So we can see that we have two different slopes when t equals negative radical 3 and when t equals positive radical 3. And so that means that we have two different tangent lines. Now both of these tangent lines occur at the point 3, 0. So the equation of the first tangent line will be y minus 0 is equal to negative radical 3 times x minus 3. And the second tangent line is going to be y minus 0 equals positive radical 3 times x minus 3. The first equation simplifies to y equals negative radical 3x plus 3 radical 3. And the second one simplifies to y equals radical 3x minus 3 radical 3. And so there are the equations of the two tangent lines. So now for part B, find the points on the curve where the tangent line is horizontal or vertical. Well, we need to remember that if the tangent line is horizontal, this implies that the slope of the tangent line is equal to 0, which implies that dy dx will be equal to 0. So in that case, we have 3t squared minus 3 divided by 2t. This is dy dx. We're going to set that equal to 0. And we know the only way a fraction can equal 0 is if the numerator of that fraction equals 0. And then from here, we can solve it a couple of different ways. I'll just factor out a 3, and then we can actually keep on factoring here. And now we're going to set each one of these factors equal to 0, and we end up getting t equals 1 or t equals negative 1. Now it says find the points on the curve where the tangent line is horizontal. So t equals 1 and t equals -1, that's not a point on the curve. What we have to do is take both of those values. So we'll start with t equals -1 and plug it in for plug it in for t in the equation to get x, and plug it in for t in the equation to get y. So x is going to be t squared, which is -1 squared, which is 1, and y is going to be t cubed, which is -1 cubed, minus 3 times t, so minus 3 times -1, and this is -1 plus 3, which is equal to 2. So this point is the point 1, 2, and then when t equals +1, x will be 1 squared, which is 1, and y will be 1 cubed minus 3 times 1, which is -2. And so this is the point 1, -2. So our horizontal tangents occur at these 2 points. Now, where is the tangent line vertical? Well, a vertical tangent occurs usually when the derivative of a function is undefined, or when the derivative goes infinite. So we have to just take a look at our derivative. So for the vertical tangent, we need dy dx basically to go to infinity. For that to happen, since dy dx is equal to 3t squared minus 3 divided by 2t, this is going to happen when we divide by 0. So if we just take the denominator 2t and set it equal to 0, we know this occurs when t equals 0. And now when I take t equals 0 and plug it into the parametric equations, we're going to get x equals 0 squared, which is 0, and y equals 0 cubed minus 3 times 0, which is also 0. So that is the point 0, 0. For part C, it says to determine where the curve is concave upward or concave downward. For this, we need the second derivative. And so the second derivative is defined to be the derivative with respect to t of the first derivative, which is 3t squared minus 3 over 2t. But then we have to divide by dx dt once again. So remember, dx dt is just 2t, right? Because we're just taking the derivative of x with respect to t. So the denominator is pretty simple. Now we just need to take the derivative of this function with respect to t, and that's going to be a quotient rule. So for that, we take the bottom function 2t, multiply it by the derivative of 3t squared minus 3, which is 6t, minus, then we take the top function 3t squared minus 3, multiply it by the derivative of the bottom function, which is 2, and then we have to divide that by the bottom function 2t quantity squared. So now let's just simplify this. We have 12t squared minus 6t squared plus 6. So here I am distributing the 2 here, and I'm also distributing the negative. This is over 4t squared, and then that whole thing is divided by 2t. So when we divide by 2t here, that's the same as multiplying by 1 over 2t. And so if I do that math there, we're going to have on the top 6t squared plus 6, and in the bottom we will have 8t to the third power. And if you want, you can simplify a little bit. We can pull out a 6, give us t squared plus 1, and then 8t cubed in the bottom. And then finally we can divide by 2, which will give us 3 times t squared plus 1 divided by 4t cubed. And this is our second derivative. Now we know that for the second derivative on our number line here, it's going to be concave up when the second derivative is positive and concave down when the second derivative is negative. So first we need to figure out, when is the numerator or denominator going to be 0? Well, we know the denominator will be 0 when t equals 0, because we can see that here. But the numerator, the t squared plus 1, is never going to equal 0. Because if you set t squared plus 1 equal to 0, you get t squared equals -1, and that means t is going to be plus or minus the square root of -1, which is plus or minus I, and imaginary numbers do not show up on the real number line. So we don't have to worry about this. So basically, you just have to test your second derivative for positive values of t and for negative values of t. And you should see that if you take a test point, like for example, if you pick t equals 4, if you plug in t equals 4, everything is going to be positive, which means the second derivative will be positive. And if you take a number like t equals -4, the second derivative is going to be negative, because when you plug in -4 here, when you raise it to the third power, you get a negative, but the numerator is still positive. So what we have then is the function should be concave down when t is less than 0, and it should be concave up when t is greater than 0. And it should be noted that anytime you say something about concavity, increasing, decreasing, etc., for parametric equations, the values that you give in these intervals are always values of t, not x. Okay, finally, we want to sketch the curve. To sketch the curve, you would graph the few important points that we brought up. So we would graph where the tangent lines are horizontal, where the tangent lines are vertical. Also, I would graph the point 3, 0, where we had the two tangent lines, and then you would simply sketch that curve. And so here is what that curve would look like. So notice we have the point 3, 0. This is where we had the two tangent lines. You can see one tangent line here is this one. The other tangent line here is this one. Those are the two tangent lines that we found earlier. And then we had a horizontal tangent when t equals -1, and that was at the point 1, 2. We had a horizontal tangent when t equals +1, and that occurred at the point 1, -2. And then we had a vertical tangent when t equals 0, and that was at the point 0, 0. So you can see that vertical tangent here. And then if you just trace out these points in order, you see that you get a curve that looks something like this. Now, of course, you can always plug in additional values of t to get additional points on the curve anytime you're trying to graph something, but this is all you need to get a sketch for this curve. In our next example, we want to find the tangent to the cycloid, which is given by the parametric equations x equals r times theta minus sine of theta and y equals r times 1 minus cosine of theta at the point where theta is equal to pi over 3. So the important thing to know here is that your function x, when we say that it's r times theta minus sine of theta, r is a constant. Theta is the parameter. And y is equal to r times 1 minus cosine of theta. So to get the slope of the tangent line, we need dy dx. We know that dy dx is dy d theta in this case, divided by dx d theta. Because again, our parameter is theta, not t. So now let's go ahead and calculate what is dy d theta. Well, we have a constant r here, and that's going to be multiplied by the derivative of 1, which is 0, and the derivative of negative cosine is negative sine, and that's going to be r times sine of theta. The negatives cancel out there. And then dx d theta is going to be r times the derivative of theta, which is 1, minus the derivative of sine, which is cosine. And so dy d theta is r sine of theta, divided by dx d theta is r times 1 minus cosine of theta. And what you see is that the derivative is independent of the size of the radius and is just equal to sine of theta divided by 1 minus cosine of theta. So now how do we find the tangent when theta equals pi over 3? Well, we find the slope of the tangent line by taking dy dx and plugging in theta equals pi over 3. So this is going to give us sine of pi over 3 divided by 1 minus cosine of pi over 3. The sine of pi over 3 is the square root of 3 over 2. Cosine of pi over 3 is 1/2. So we end up with the square root of 3 over 2 divided by 1/2, which is equal to the square root of 3. Now that's the slope of the tangent line. But if you want to actually find the tangent line, the equation of the tangent line, you need x and y. And so x is going to be the point r times theta, right? Theta is pi over 3 minus the sine of theta, which is pi over 3. And y is equal to r times 1 minus the cosine of pi over 3. And so this is equal to r times pi over 3 minus square root of 3 over 2, and the y-coordinate is r times 1 minus 1/2, which is r over 2. And now we just take the x value and the y value and the slope, and we plug it all into the equation of a line, and that gives us this very complicated equation. And you could multiply this out a little bit, I suppose. You could multiply radical 3 times x, and then radical 3r times pi over 3 minus square root of 3 over 2. And then you could add r over 2 to both sides. I don't really know if this makes the equation of the tangent line any nicer. Let's see here. So if I multiply that, I get that. Negative times negative is positive. Radical 3 times radical 3 is 3r over 2 plus r over 2. I suppose it does get a little bit nicer. This is going to be 4r over 2, which is 2r. Now for the second part, it says, at what points is the tangent horizontal and when is it vertical? So let's go ahead and bring dy dx back in. And then we need to remember, what does it mean for a tangent to be horizontal? If the tangent is horizontal, it means dy dx is equal to 0. And when is it vertical? It means that dy dx is undefined. So when is dy dx going to be 0? That's going to happen when the numerator is 0. And when is dy dx going to be undefined? That will happen when the denominator is 0. Now we're only going to do this from 0 to 2 pi. And so when is sine equal to 0 from 0 to 2 pi? Well, that's going to be when theta is 0, pi, or 2 pi. And then if 1 minus cosine of theta equals 0, this is the same thing as saying cosine is equal to 1, and cosine is equal to 1 at 0 and 2 pi. So what does this mean? Well, I want you to notice that when theta equals 0 and 2 pi, both the numerator and the denominator is equal to 0 in your derivative. So you have 0 divided by 0. So we don't know if those are going to be horizontal or vertical. So again, the horizontal normally occurs when the top is 0, right? And the vertical occurs when the bottom is 0. But if both the top and the bottom of the fraction are 0, it takes further analysis. So all we know right now is that at pi, we have a horizontal tangent. Okay, so now we got to say what happens at 0 and what happens at 2 pi. So for this, we're going to take a limit as theta approaches 0 of our derivative, sine of theta divided by 1 minus cosine of theta. And again, we know this is going to give us 0 divided by 0. So using L'Hopital's rule, we can take the derivative of the top divided by, and then the derivative of the bottom. So the derivative of negative cosine is sine. And then we'll take the limit as theta goes to 0 again. And this is going to give us 1 divided by 0, which is essentially infinity. Now, technically, you have to approach 0 from the left and 0 from the right. But what you will notice is that we get a vertical tangent here when you do that. Now, the same thing happens when you take the limit as theta approaches 2 pi. Because when you approach 2 pi, you have the same functions, and you are going to get 0 divided by 0 again. And so we'll take the derivatives again, using L'Hopital's rule, and you will once again get 1 divided by 0. Okay, and technically, again, you get plus or minus infinity depending on if you're coming from the left or coming from the right. So what does that mean? Well, it means that when theta is 0 or 2 pi, the derivative is undefined, and therefore you have a vertical tangent. Okay, so what points are those going to be on the curve? Well, all you have to do is plug in theta equals 0 and 2 pi and pi into your original equations to get the points on the curve, and we'll go ahead and take a look at the graph. So first, let's just look when theta equals pi over 3, which is right about here. You can see that we had that tangent line there, and you can also see that we have a horizontal tangent when theta equals pi. Okay, so this is pi right in the middle here. And then you can see that we have a vertical tangent when theta equals 2 pi. Okay, that's what happens right here. And of course, also when theta equals 0, you have a vertical tangent here. And actually, at any even multiple of pi, you're going to have a vertical tangent. And any odd multiple of pi, you are going to have a horizontal tangent, because the cycloid, of course, repeats over and over again. Now let's talk about areas under a curve. So we know that the area under a curve y equals f of x from a to b is area equals the integral from a to b of f of x dx, as long as our function f of x is positive. If the curve is traced out once by the parametric equations x equals f of t and y equals g of t for t between two values alpha and beta, then we can calculate the area by making substitution. So we start with the basic concept that the area is the integral from a to b f of x dx, but then you can think of that as the integral from a to b of y times dx, because y is equal to f of x. But then we also know that y is equal to the parametric equation g of t, and x is equal to the parametric equation f of t, and that means that dx will be f prime of t dt. So I can replace dx with f prime of t times dt, and then we change the values from a to b to alpha to beta. All right, and so the integration formula for finding the area when given parametric equations is this formula right here. Now you will notice that it also says, or it might be this formula. Well, that all just depends on how the curve is traced, okay? So let's talk just a little bit more about that, and then we'll move on to an example. So if you have a parametric curve that is traced like this, okay, where this is t equals alpha and this is t equals beta, so notice that as t increases, x is also increasing from a to b, then it's just the formula you see here. But if for some reason when you trace your curve, if t equals alpha is up here and t equals beta is down here, in other words, if the curve is traced in the opposite direction, then you are moving from x equals b to x equals a in the other direction. And in that case, you need to use this formula. So the bottom line is this. If you find the area using this formula here and you get a negative number, it's because this is happening. And the way you fix it is you just switch your limits. So you take your alpha and your beta and you literally just switch them. So in this example, we want to find the area under one arch of the cycloid. So let's remember what the cycloid looks like. So the cycloid is the curve that looks something like this. And this corresponds to t equals 0. The top here corresponds to t equals pi, and the other side here corresponds to t equals 2 pi. So to find the area under the curve, notice that the orientation of this curve is going from left to right. So we should just be able to take the integral from t equals 0 to t equals 2 pi. And then we should take our function g of t, which is r times 1 minus cosine of theta. And then we need to take f prime of t, or dx dt. So dx dt is going to be r times 1 minus cosine of theta, which coincidentally is the same thing here. Okay? And so again, this was y, and this was dx dt, or dx d theta, I should say, not dt, because the variable, the parameter here is theta. Okay? So now we're going to go ahead and do this integral. We have r squared, which can be factored out of the integral. And then we have 1 minus cosine of theta times 1 minus cosine of theta, which is 1 minus cosine of theta quantity squared. And now from here, we're just going to multiply out 1 minus cosine of theta squared, which gives us this. So we're doing a little bit of FOIL there. And then we'll go ahead and find these antiderivatives. So the antiderivative here is just theta. The antiderivative of negative 2 cosine of theta is negative 2 sine of theta. And then what about the antiderivative of cosine squared? Well, we have to remember that to do that, we have to use a half angle identity. Cosine squared of theta is 1 plus the cosine of 2 theta divided by 2. So we can think of that as 1/2 plus 1/2 cosine of 2 theta. So when we take the integral of cosine squared, we are just taking the integral of this. And so the integral of 1/2 is going to be 1/2 theta plus 1/2, and then what is the integral of cosine of 2 theta? It is 1/2 sine of 2 theta. And this goes from 0 to 2 pi. So now let's combine like terms. We have theta plus 1/2 theta, which is 3/2 theta, minus 2 sine of theta, plus 1/2 times 1/2 is 1/4 sine of 2 theta, from 0 to 2 pi. So now let's plug in 2 pi. We have r squared times 3/2 times 2 pi, minus, when you plug in 2 pi into here, you're going to get 0. When you plug in 2 pi into here, you're also going to get 0. Minus, and then when you plug in 0 into all three of these, you're going to get 0 for all of those as well. So what we have is r squared times 3/2 times 2 pi, which is 3 pi, which ends up being 3 pi r squared. Next, we'll talk about arc length. So if we have a curve defined by parametric equations, x equals f of t and y equals g of t, t between alpha and beta, f prime and g prime are continuous, then the arc length is given by the formula integral from alpha to beta square root of dx dt squared plus dy dt squared, and then with respect to t. And we do have to assume that the curve is traversed only once as t increases from alpha to beta. So if the curve is traversed multiple times, then this will not give you the arc length. It will give you a multiple of the arc length. So let's go ahead and take a look at an example. Here we want to find the length of the curve defined by the following parametric equations. X equals e to the t minus t, y equals 4e to the t divided by 2, where t is between 0 and 2. So we know that the formula for the arc length is L equals integral from alpha to beta, square root of dx dt quantity squared plus dy dt quantity squared. It's the square root of that whole thing, and then with respect to t. So we need dx dt. Well, the derivative of e to the t is e to the t minus the derivative of t is 1. So that was easy enough. We also need dy dt. The derivative of 4e to the t divided by 2 is 4e to the t divided by 2 times the derivative of t divided by 2. And the derivative of t divided by 2 is 1/2. So we end up getting 2e to the t divided by 2. So now the arc length is going to be the integral from t equals 0 to t equals 2 of the square root of dx dt, which is e to the t minus 1, quantity squared, plus dy dt, which is 2e to the t divided by 2, quantity squared, dt. So now we need to go ahead and multiply this out. E to the t minus 1 squared means e to the t minus 1 times e to the t minus 1. This gives us e to the t times e to the t, which is e to the 2t, because we're adding those together. And then we have minus e to the t times 1 minus e to the t times 1, and then negative 1 times negative 1 is positive 1. And so ultimately we have e to the 2t minus 2e to the t plus 1. And then we also need to do 2e to the t divided by 2 squared. And here we're just going to square each one of these. And so we're going to get 4e to the t. So when you square here, you're multiplying these together, and these 2's cancel out. And so now we can put this all back into the integral. We have the integral from 0 to 2. We have the square root of this plus this. And what we can do here, of course, is combine. Negative 2e to the t plus 4e to the t is positive 2e to the t. And then from here, this is not a very intuitive part, but I want to show you that this came from squaring this. This is very similar to this. In fact, the only difference is now we have a positive here instead of this negative. So this is going to factor exactly like this, except that we will have a plus sign here. And so this becomes the integral from 0 to 2 of the square root of e to the t plus 1 squared. And now we just have the square root of a square, which cancels. So we end up with just e to the t plus 1. Now don't forget, you still have to take the antiderivative, which is going to be e to the t plus t. And this goes from 0 to 2. And so we will get e squared plus 2 minus e to the 0 plus 0. And this is e squared plus 2 minus 1, which is e squared plus 1. So lots of algebra involved here. The formula is not terribly hard to remember, but you got to make sure that you do all these little steps correctly. Next, let's find the length of one arch of the cycloid. So we are once again using the arc length formula, integral from alpha to beta, square root of, in this case it's going to be dx d theta squared plus dy d theta squared, and then with respect to theta. So let's calculate dx d theta. This is going to be r times 1 minus cosine of theta. So keep in mind that r is a constant, so we're just taking the derivative with respect to theta of each of those. And then dy d theta, same idea. We're going to have r times negative sine of theta. You might remember that we took these derivatives just a few moments ago. And so now the arc length is going to be the integral. One arch of the cycloid occurs from 0 to 2 pi, and then we're going to have the square root of dx d theta, quantity squared, plus, and then dy d theta, quantity squared, and d theta. So now let's just go through and do the multiplication here. So we're going to have r squared times 1 minus cosine times 1 minus cosine, and that's going to be r squared times 1 minus 2 cosine theta plus cosine squared of theta. And then the other one here is just going to be r squared sine squared. So now in the radical we are adding this and this. So our arc length becomes the following. R squared, let's multiply this out. We have r squared times 1. Actually, I take that back. Let's not multiply that out. Let's leave it as is. You can do it either way, actually. Okay, so this is what we have. Now from here, what we're going to do is we're going to factor the r squared here and here completely out of the radical. And when you do that, you're going to get an r out in front. And inside the radical, we have 1 minus 2 cosine theta plus cosine squared theta plus sine squared theta d theta. And now we need to remember that cosine squared of theta plus sine squared of theta is 1. And then this is also 1. And if we add 1 and 1 together, we're going to get 2. So this becomes r times the integral of the square root of 2 minus 2 cosine theta d theta. Okay, next up, we are going to factor the 2 out. First, we'll do that inside the radical, which gives us this, and then we'll pull it out of the radical as a radical 2. So we're going to have r times radical 2, integral from 0 to 2 pi, and then the square root of 1 minus cosine of theta d theta. Now this next step is going to be really tricky. So the question is, how do we integrate this? We don't have a du, so we can't let u equal this. What we have to do is use a trig identity. So we know that sine squared of theta divided by 2 is 1 minus cosine of theta all divided by 2. Or we can say 2 sine squared of theta divided by 2 is equal to 1 minus cosine of theta. So if I have the square root of 1 minus cosine of theta, that's going to equal the square root of 2 sine squared of theta. And that is going to be the square root of 2 times the square root of sine squared of theta over 2. Now this is where it gets a little bit tricky. The square root of sine squared of theta over 2 is the absolute value of the sine of theta over 2. So this here gets replaced with this. And so this becomes r radical 2 integral 0 to 2 pi radical 2 times the absolute value of the sine of theta over 2. Now when you pull this radical 2 out here, radical 2 times radical 2 is going to be 2. So we will have 2r integral from 0 to 2 pi absolute value of the sine of theta over 2. Now how do you integrate an absolute value? Well, it depends on whether this function is positive or negative. So let's think about the sine function. We know the sine function looks like this. But if you have y equals sine of theta divided by 2, the period of this sine function is 4 pi. So out here, this is 4 pi, and right here, this is 2 pi. So what I want you to notice is that y equals sine of theta over 2 is above the x-axis from 0 to 2 pi. What that means is that we can remove the absolute values here. We don't need the absolute values. And I'm also going to change theta over 2 to be 1/2 theta. Okay, almost done. So now we need to take the antiderivative. Well, remember, the antiderivative of sine of ax dx is negative 1 over a cosine of ax. So in this case, it's going to be negative 1 over 1/2 cosine of 1/2 theta. And so this is negative 4r cosine of 1/2 theta. And then we have to go from 0 to 2 pi. And of course, this is equal to negative 4r times the cosine of 1/2 times 2 pi minus the cosine of 1/2 times 0. And this is negative 4r times the cosine of pi minus the cosine of 0. And this is negative 4r times negative 1 minus 1, or negative 4r times negative 2, which is 8r. Before we go on to the final topic, let's look at a special application of parametric equations. We can find the speed of a particle if the position is given in parametric form by using the following formula. V of t is equal to the square root of dx dt quantity squared plus dy dt quantity squared. In the following example, the position of a particle at time t is given by the parametric equations x equals 2t plus 3 and y equals 4t squared for positive values of t. Find the speed of the particle when it is at the point x equals 5, y equals 4. To do this, the first thing we need to do is calculate the derivative dx dt, which is 2, and the derivative dy dt, which is 8t. Now, using the formula, we know that v of t is the square root of 2 squared plus 8t squared. And this is the square root of 4 plus 64t squared. So now to get the speed, we need to plug in the appropriate value of t, but we weren't given that. We were given the point x equals 5, y equals 4. We know that x is equal to 2t plus 3, and so if x is going to be equal to 5, we can set this equal to 5 and solve for t. And when we do that, we get t equals 1. Likewise, y is equal to 4t squared. And in this problem, they tell us that y is 4. So if we set this equal to 4, we can also solve for t here, which will give us plus or minus 1. But we need to remember that t can only be positive, right? Because they tell us that right here. And so I'm just confirming that t equals 1 does indeed give us the point x equals 5, y equals 4. And so now to find the speed, all I need to do is substitute the value t equals 1 in here. And when we do this, we get the square root of 68, which can be simplified to 2 radical 17. The final topic is finding the surface area revolving a curve about the x-axis using parametric equations. Here's the formula for doing that. If you look closely, you'll notice that this formula is very similar to the formula that we learned using rectangular equations. So in this example, we have x equals 2t squared plus 1 over t, and y equals 8 radical t. T is between 1 and 3. And we want to find the surface area when revolving this curve about the x-axis. This is pretty much just a matter of plugging the information into the formula and then doing the integral. So first, let's calculate dx dt. We know that dx dt is 4t minus 1 over t squared. And dy dt is equal to 8 times 1 over 2 radical t, which is 4 divided by radical t. Now let's go ahead and figure out the radical part of this. So we're going to have the square root of dx dt squared plus dy dt squared. And now we just need to simplify this expression as much as possible. So if we multiply this out, we're going to get the square root of 16t squared minus 4 divided by t minus 4 divided by t plus 1 divided by t to the 4th power plus, and then when we do this one here, we get 16 over t. Now, you might need to pause the video right now and verify that when you multiply this out, you do indeed get this. Okay, so if you verified that, then let's go ahead and continue. So now this is equal to the square root of 16t squared, and I'm going to combine all of these together because they are all like terms, and this will give us plus 8 over t, and then plus 1 over t to the 4th. The next step is perhaps the trickiest one of all, but this will factor very much like this, except that instead of having a negative like you have here, you will have a positive. So this becomes the square root of 4t plus 1 over t squared, quantity squared. And this simplifies to 4t plus 1 over t squared because the radical and the square here cancel out. So that is this part of the integration. So now let's go ahead and plug in everything else. This becomes the integral from t equals 1 to t equals 3. We have 2 pi multiplied by y, which is 8 radical t, multiplied by this radical, which we just simplified down below, is 4t plus 1 over t squared. And now we just need to finish this integral. So what we have here is 16 pi integral from 1 to 3. And now I'm going to multiply radical t times 4t. That's going to be 4t to the 3/2 power. And then radical t multiplied by 1 over t squared. That's going to be radical t divided by t squared, which simplifies to t to the negative 3/2. dt. Now we'll just go ahead and use the power rule. So 16 pi multiplied by 4 t to the 5/2 divided by 5/2 plus t to the negative 1/2 divided by negative 1/2. And this goes from 1 to 3. Now, of course, we want to simplify here. So we have 16 pi. Inverting and multiplying the 5/2 here is going to give us 8/5 t to the 5/2. And then we get minus 2 t to the negative 1/2, which can be written as 2 divided by radical t. Okay, so now we need to plug in our limits. If I plug in 3, we get 16 pi multiplied by 8/5 times 3 to the 5/2 minus 2 divided by the square root of 3 minus, and if I plug in 1, we're just going to get 8/5 minus 2. Now we just need to simplify. So let's think about 3 to the 5/2 power. This is the square root of 3, quantity to the 5th power, which simplifies to 9 radical 3. So this becomes 16 pi 8/5 times 9 radical 3 minus, this can be rationalized, 2 radical 3 over radical 3. And then 8/5 take away 2 is negative 2/5, and then the negative changes to a positive 2/5. Oops, and this is a 3 here. There we go. All right, let's keep going. We have 16 pi, 72 radical 3 over 5 minus 2 radical 3 over 3 plus 2 over 5. I'm going to get a common denominator, which is going to be 15 by multiplying by the appropriate number. And this will give us 16 pi multiplied by 216 radical 3 over 15 minus 10 radical 3 over 15 plus 6 over 15. And one last simplification step here. We can combine these two. 216 radical 3, take away 10 radical 3 is 206 radical 3. And then we have plus 6 all over 15. And the last thing you can do is you can factor out a 2 here, which is going to give you 32 pi multiplied by 103 radical 3 plus 3 all over 15. And this is about as good as we can make this answer look. And that concludes this video lesson.